Hello, and welcome to my individual presentation on question 4 based around gases. So, for the first part of this question, it asks us to calculate the pressure of 255 grams of neon gas at 122 Kelvin in a 3 decimeter cube container using the ideal gas law. So, we first need to introduce the ideal gas law, and this is PV is equal to nRT. And this equation represents a perfect gas system. Now, by a perfect gas system, it's where we satisfy the following conditions. All of the collisions in the system are completely elastic. There are no interactions between gas particles, and the gas particles have a zero equivalent in volume. Now, by completely elastic collisions, we mean that whenever there were to be a collision between, say, two gas particles, there will be no loss in their kinetic energies, and therefore no change in their speeds, and the pressure of the system will therefore remain constant. And considering the fact that there are no interactions between gas particles, we can see that from this quick animation here, that the particles do not interfere with one another's paths of journey, and they continue like one another are not present, and this again leads to no changes in the pressure. The final assumption is based around the fact that the gas particles have a zero equivalent in volume, and what this tells us is that the particles are free to move throughout the entirety of the container, like so in this small animation here. Even though this animation doesn't overly justify this point, if you were to take into account other gas particles being in this system, then it would be as such that the gas particles will still occupy this whole volume here, even though in reality they can't. So we can now start on the calculation of the pressure. Given the fact that we have the mass of neon in the system, we can calculate the moles, and in this case the number of moles is 12.6. We also know the temperature and the volume and also the gas constant R. But by looking at the units of R, then it must be such that the units of volume must be in meters cubed. And when we do that little conversion, we get the units of volume in meters cubed, and it gives us a value of 3/1000th of a meters cubed. Now, subbing these values into the ideal gas law and rearranging, we can see that using all of these units, they should just cancel down. So the moles cancel with the moles, kelvins with the kelvins, and the meters cubed with the meters cubed, leaving us with a unit of pressure, which is the Pascal. And after calculation, we are left with a value of pressure that is around 4.26 million pascals. But what is pressure? It's a unit that represents the force per unit area, which is slightly illustrated by this animation here. As you can see, the particles are colliding with the surface and are exerting a force upon it. Now, by looking at the ideal gas law, we can see that either via increasing the temperature or the number of moles of a gas, given a constant volume, we will see an increase in the pressure of the system due to the proportionality. The reason being is that when you have more moles of a gas, what it ultimately means that there are more particles of that gas in the system, or in a given volume, and therefore there'll be a greater number of collisions and a greater force produced. An increased temperature means that the gas particles will have more energy, and when they have more energy, they'll have a greater velocity, and they'll therefore be colliding with or exerting a greater force on a surface in comparison to gas particles that are at lower temperatures. Continuing, we are now asked to calculate the pressure given the gas behaves as a van der Waals gas. So this is the van der Waals equation for a gas. But when we take this equation, we now have to take into account a couple of important factors. One of which being is that the gas particles will now actually have some form of volume, and the other being is that the gas particles will interact with one another. So, in terms of gas particles having a volume, it can't be the fact that each particle occupies the whole container, but some of it. As shown here, if you look, it can't be such that this gas particle occupies this voluminous space at this instant in time. And by looking at the van der Waals equation for a real gas, the actual volume itself would be the volume, but take away the number of moles multiplied by a constant b that is dependent upon the gas we have. We can also see from this that the smaller the volume becomes, the more pronounced this correction actually becomes. Although, with gas particles interacting, there would actually be some interference with the paths in which they travel this time, like so. And due to the attraction decreasing the force at which the particles collide with the surface, the pressure of the system would be lower than expected. This is shown by this small correction factor, where A is a constant that is dependent upon the gas itself, and it is positive to make up for the fact that we now have these interactions occurring in the system. Now onto the calculation. We start by subbing in all of our values into the van der Waals gas equation to come out with this pretty lengthy looking equation. But as we can see again, units will quickly start to cancel. So decimeters with decimeters and moles and so on. But we do need to remember our conversion of decimeters into meters cubed again to remain consistent with the units. Although after further rearrangement we can see that we have another issue with the units, and this time it's with pressure. So a quick look at this sample conversion chart here, and we can see that via a division of 0.987 and a further multiplication of 3.62, we will yield the pressure of atmospheres into pascals. Now subbing this back into the equation, we will yield an actual pressure of the system to be around 4.2 million pascals. Now what this pressure really represents is the pressure given that we have taken into account the reduction in volume and the decrease in pressure via the gas particles interacting with one another. Now part 2 of this question tells us to calculate the partial pressure of helium gas, given we add 40 grams of itself to the system at the same pressure. So given we are assuming ideal gas behaviour, we know that this ideal gas pressure is going to be around 4.3 million pascals from the previous part of this question. We also know the mass of the helium, and therefore we can get the number of moles of helium to be around 10. Also taking into account neon's 12.6 moles, then we can say that the total number of moles of gas in this system is around 22.6 moles. So we can now start to move on to working out the mole fraction of helium gas. This is simply a case of working out how much of the system is dominated by a certain gas. So in terms of helium, we can say that the mole fraction of helium is going to be its 10 moles divided by the total of 22.6 moles to give a mole fraction of 0.442 in this system. So now we can work out the partial pressure of the helium gas, which is simply multiplying the mole fraction by the total pressure in the system to give us a partial pressure of helium gas to be around 1.9 million pascals. What this ultimately tells us is that 1.9 million pascals of this pressure is actually accounted for by the helium gas, and the rest is accounted for by the neon gas. The final part of this question revolves around determining the Maxwell-Boltzmann distribution for both helium and neon in this system. This also includes the calculation of their root mean square speeds. So we can determine 3 different speeds for the Maxwell-Boltzmann distribution, as it's a graph of the number of molecules against their speeds. These 3 speeds are the maximum speed, the mean speed, and the root mean square speed. So for neon, we can start subbing in our values firstly into the maximum speed at which molecules can obtain. We want this speed to be in meters per second, but to eliminate the joule unit in R, we can break it down into its SI units, being kilogram meter squared per second squared. And we can also see that the units for the MR of neon are in grams per mole, so a conversion of this into kilograms per mole should do the trick. You'll ultimately end up with a speed of around 317 meters per second. For the mean speed, we'll come up with around 358 meters per second, and for the root mean square speed, it'll come up to be around 388 meters per second in this case. So we can now start to move on to helium. Again, we can apply the exact same method here with unit conversions, and we will get the following speeds. So to plot the Boltzmann distribution for each gas type, we need to take into account their relative sizes. And as neon is a heavier type of atom than helium, we need to realize that due to this difference in mass, the neon atoms will attain a lower maximum speed than the helium atoms will at a certain temperature. The range of speeds at which more atoms can also attain will be much less than in comparison to helium-2. And we can see that from the equation to speed, there's that inverse proportionality between the speed and the molar mass. So therefore, as the molar mass increases, the speed will ultimately decrease, or the speeds will decrease. So drawing neon's distribution, we can exaggerate this point by making the graph of neon a lot more steeper than in comparison to helium's distribution to show that the helium atoms will attain a greater number of atomic speeds and a greater maximum like shown. Hopefully all of these questions were answered in sufficient detail, and thank you for watching.